Welcome, dear travelers of the mind, to Conscious Frequency. It's a profound joy to share this space with you, a sanctuary for contemplation and discovery. Here, we aim to peel back the layers of the universe's wonders, not with a harsh light, but with the gentle glow of inquiry and a touch of scientific poetry. Today, we embark on a voyage to the very edges of our comprehension, to explore a concept so profound, so alien it might as well be woven from starlight and dreams as strange matter. This isn't merely matter as we know it, the familiar dance of protons, neutrons, and electrons. No, this is a whisper from the universe's deepest secrets, a testament to the boundless imagination of physics, a realm where the very building blocks of reality might be different. It's a journey into the truly unknown, where our deepest scientific questions might just find their answers, wrapped in an enigma. As we begin this exploration, I invite you to find your most comfortable space. Perhaps you're nestled in a quiet corner, the world outside hushed, or maybe you're watching the dawn break, painting the sky with soft hues. Wherever you are, know that you are connected to a vast tapestry of curiosity, a shared moment of wonder. Feel free to share a whisper of your location in the comments below, if you feel so inclined. It's always a delight to feel the presence of so many kindred spirits. If this journey into the unknown, this gentle probing of the cosmos, speaks to your soul, consider joining our growing constellation of curious minds by subscribing. It's a gentle way to ensure these explorations continue to find you, like a comforting echo in the cosmic silence, a quiet invitation to keep wondering together. Over the next 2.5 hours, we will slowly, deliberately, unfurl the mysteries of strange matter. We'll dive into its theoretical underpinnings, its potential manifestations, and the philosophical questions it ignites, like sparks from a celestial fire. So, take a deep, slow breath, let the outside world recede for a little while, and allow yourself to be fully present for this unfolding. Let's begin. We've set our intention. Now let the cosmic currents guide us, as we begin to perceive the faintest echoes of the truly extraordinary. We spend our lives interacting with the world through our senses, don't we? We touch, we see, we hear, we taste, we smell. And what we perceive, what we can measure with our most sophisticated instruments, is this beautiful dance of atoms and molecules. Protons, neutrons, electrons, all spinning in their predictable orbits, forming the very fabric of the chair you're sitting on, the air you're breathing, even the thoughts flickering through your mind. It's a familiar, comforting universe, built on these fundamental building blocks. But what if that's just the tip of the iceberg? What if our everyday experience, as rich and vibrant as it is only a whisper of the full symphony of existence? Our senses, bless them, are magnificent, but they are also exquisitely tuned to this particular reality. They're like perfectly crafted instruments, designed to play a specific melody, but perhaps not the entire orchestral score. And our scientific instruments, while pushing the boundaries of what we can detect, are still extensions of those senses, still operating within the framework of what we expect to find. We're like deep sea divers, meticulously charting the coral reefs and the shimmering schools of fish near the surface, but the true, ancient leviathans of the abyss, they might be swimming in realms our current equipment can't even begin to illuminate. This is where the idea of exotic matter begins to unfurl, like a strange, iridescent bloom in the dark. It's the notion that matter itself can exist in forms far, far removed from our familiar protons, neutrons, and electrons. Matter that might not play by the rules we've so painstakingly learned. Imagine matter that's not bound by the usual forces, or perhaps bound by entirely new ones we haven't yet discovered. Matter that might be incredibly dense or impossibly diffuse, or even exist in states that defy our very understanding of space and time. It's a concept that stretches the imagination, isn't it? And this isn't entirely a new thought, not really. Even in the early days of quantum mechanics and relativity, as physicists began to probe the very edges of reality, they stumbled upon theoretical possibilities that hinted at this strangeness. Concepts like negative mass, or matter composed of entirely different fundamental particles, or even matter that could exist in multiple dimensions simultaneously. These weren't just wild fantasies, they were logical extensions of the mathematical frameworks that were so successfully describing our universe. They were like faint glimmers of light from a distant galaxy, suggesting there was more out there than we could immediately see. So, why are we drawn to these seemingly abstract, almost ethereal ideas? Why do scientists, the meticulous cartographers of the cosmos, spend their precious time pondering these theoretical frontiers? It's that inherent human drive, isn't it? The insatiable curiosity that whispers in our souls, urging us to look beyond the horizon to ask, what if? It's the same spark that drove our ancestors to gaze at the stars and wonder. It's the allure of the unknown, the irresistible pull of the mystery. Because within these theoretical boundaries, within these whispers of the unconventional, lies the potential for a deeper, more profound understanding of everything. It's like a cosmic puzzle, and we're just starting to find some of the most peculiar, most fascinating pieces. Imagine the universe as a vast ocean. We've spent ages charting the surface waves, the predictable tides, the familiar currents that carry our ships. But what lies in the unfathomable depths, in currents we can't yet feel or see? What strange, beautiful, and perhaps even terrifying forms of life, or matter, might be dwelling in those unseen realms? But what specific conditions might necessitate such extraordinary forms of matter? Our next chapter delves into the very crucible of existence, exploring the extreme environments where the ordinary might simply break. What is one question about the universe that keeps you awake at night? From the subtle hints, we now turn to the intense environments where the familiar can break apart, paving the way for the truly strange. We've been talking about the building blocks of everything, those fundamental particles that whisper the secrets of reality. But what if I told you that some of these building blocks aren't quite as solid as we might imagine? At least not always. Let's dive into the heart of matter, into a realm where things get squishy. Meet the quarks. These are the truly fundamental pieces, the ultimate Lego bricks. They're the stuff that makes up protons and neutrons, the very core of the atoms that form you, me, this microphone, the air we breathe. But here's the peculiar thing. Quarks don't typically exist on their own. They're like shy little creatures, always found in pairs or triplets, bound together by an incredibly powerful force. This is the strong nuclear force, and it's, well, strong. Imagine trying to pull apart two magnets that are pressed together with the force of 1,000 suns. That's a bit like trying to pull a quark away from its companions. The further you try to pull them, the stronger the force becomes, as if the universe itself is saying, nope, you're staying together. This is called confinement. Now, let's rewind. Way back. To the very, very beginning. Moments after the Big Bang, the universe wasn't the cool, calm, collected place we see today. It was an inferno, a searing, seething cauldron of unimaginable energy and heat. Temperatures were so high, so incredibly intense, that even the strong nuclear force couldn't hold things together in the way we're used to. Protons and neutrons, those familiar clusters of quarks, couldn't form. Instead, the quarks, along with their energetic messengers, the gluons, were all just free. Imagine a vast, boundless ocean not of water, but of pure, unadulterated quarks and gluons, swirling and interacting, a cosmic soup of fundamental particles. This state of matter is what scientists call a quark-gluon plasma. It's a state where the usual rules of confinement are temporarily suspended, and these fundamental pieces can roam unbound. Think of quarks like individual beads that are usually strung tightly onto a necklace, like a proton or a neutron. In the early universe, the necklace broke, and the beads were scattered freely, dancing in a vibrant, energetic soup, before the universe began to cool down. As the cosmos expanded and cooled, like a hot drink slowly losing its steam, the energy levels dropped, and as that energy receded, the powerful embrace of the strong nuclear force began to reassert itself. The free quarks and gluons started to clump together, to form those familiar triplets and pairs. They zipped into protons, they nestled into neutrons, and slowly, painstakingly, the first atoms began to form. The universe was still incredibly hot, mind you, but it was cooling enough for the familiar structures of matter to emerge from that primordial, unbound state. But here's where the contemplation deepens. What if those conditions, that unbound state of quark-gluon plasma, could be recreated? What if we could, for a fleeting moment, engineer an environment hot and dense enough to break apart the strong nuclear force, to unleash those quarks from their confinement, It's not just a theoretical playground, scientists are actually doing this. By smashing atomic nuclei together at incredibly high speeds in massive particle accelerators, they can briefly recreate those fiery moments from the early universe. And in doing so, they observe this fleeting quark, gluon plasma, a glimpse into the universe's infancy. And this leads us to a truly fascinating thought: if matter can exist in such a free-form state, unbound into protons and neutrons, could it also aggregate in ways that defy our expectations of stability? Could there be other, stranger forms of matter, born from this unbound potential, that we haven't even dreamed of yet? Imagine matter that isn't organized into the neat, tidy packages of atoms, but exists as a vast, interconnected sea of fundamental forces and particles, held together by their own inherent, perhaps even conscious, interactions. It's a mind-bending idea, isn't it? A universe where the very definition of stuff can shift and transform, from tightly bound collections to a wild, unbound dance. If you could witness the early universe, that moment just after the Big Bang, that quark, gluon plasma, what element of it would you most want to observe? What would you hope to feel, to understand, from that initial, unbound explosion of creation? The name itself, strange, hints at a departure from the ordinary. Let's explore what strangeness truly means in the language of particles. Imagine the fundamental building blocks of our universe, the quarks, as a rather exclusive club. We've met the up and down quarks, the common, everyday members, like the comfortable hum of a refrigerator. They're the most stable, the most frequently encountered. But then, there's another member, a bit more elusive, a touch more different. This is the strange quark, often symbolized with a little s. It's like finding a perfectly formed, iridescent seashell on a beach where you only expected pebbles. Now, this strange quark isn't just a different label. It carries a different weight, a more substantial heft. It's significantly heavier than its up and down cousins, like a finely crafted, antique pocket watch compared to a simple plastic one. This extra mass is a key part of its character, a subtle gravity that influences the particles it joins. But the real magic, the true essence of its strangeness, lies in how it interacts, or rather, how it doesn't interact as readily as the others. You see, in the quantum world, there are certain rules, certain cosmic accounting principles. And one of these principles is conservation. Think of it like a closed system where energy, or in this case, a specific quantum property, can't just vanish. It has to be accounted for. This property, this invisible tag that the strange quark carries, is called strangeness. It's a quantum number, a label assigned to particles that contain this peculiar quark. And here's the fascinating part: in many of the fundamental forces, like the strong nuclear force that binds protons and neutrons together, strangeness is conserved. It's like a secret handshake that only certain particles know. If a particle starts with strangeness, any interaction governed by the strong force will ensure the resulting particles also have a total strangeness that adds up. However, when the weak nuclear force comes into play, that subtle, almost shy force responsible for radioactive decay, things get a little more interesting. The weak force can change strangeness. It's like a loophole in the cosmic accounting, allowing a particle carrying strangeness to transform into something else, something that might not have that characteristic. This is where we first encountered this concept. Scientists observed certain particles that seemed to live a surprisingly long time before decaying. They were produced in high-energy collisions, suggesting they contained these new, exotic quarks. But their decay was much slower than expected, a lingering presence that defied the usual rules. These particles, like the gluons and hyperons, were like unexpected guests who stayed a little too long at the party. Their unusual lifespan, their slow departure from the observable universe, was the first clue that something strange was at play. Strangeness is like a unique ingredient in a recipe. When it's present in a particle, that particle behaves differently, decaying in ways that are unexpected if you only have the common ingredients. It's like adding a pinch of saffron to a simple bread dough. The flavor, the aroma, the very way it transforms in the oven, becomes something entirely new. This discovery, this understanding of the strange quark and its associated quantum number, wasn't just a curious footnote. It was a profound expansion of our theoretical playground. It opened up entirely new avenues of thought. If particles with this strange property exist, and if this property is conserved in certain interactions, could they combine in ways that create entirely new, stable forms of matter? Matter that, by its very nature, is built upon this fundamental strangeness. This is the question that truly began to whisper in the halls of physics, hinting at possibilities we hadn't even dared to imagine. This leads us to the heart of our exploration, the hypothetical entities that embody the strange in its most fundamental form. We're talking about strangelets. Now, that word itself, strangelet, it sounds like something out of a whimsical fairy tale, doesn't it? A tiny, peculiar creature from a land we can only imagine. But in the realm of particle physics, it points to something far more profound, and perhaps even more alien. So, what exactly is a strangelet? Imagine, if you will, the very building blocks of matter, the quarks. We're familiar with the up and down quarks, the ones that make up the protons and neutrons in every atom around us. But the universe, in its infinite generosity, offers a whole spectrum of these fundamental particles. Among them is the S-strange quark. A strangelet, in its purest, most theoretical form, is essentially a tiny, hypothetical lump of matter composed of roughly equal numbers of these up, down, and strange quarks. Picture it like a cosmic stew, where the ingredients are these fundamental particles, and the recipe calls for a perfect, almost impossible balance. Now, here's where things get truly mind-bending, where the ordinary begins to shimmer and transform. The truly revolutionary idea, the one that makes physicists' eyes widen with a mix of awe and trepidation, is the stability hypothesis. It proposes that such a collection of quarks, this strangelet, might not just be a fleeting anomaly, but could actually be more stable than the ordinary nuclear matter we know and love, the protons and neutrons that hold our universe together. Think about it. Our familiar matter, the stuff of stars, planets, and ourselves, is built from up and down quarks. But this hypothesis suggests that by introducing a significant, balanced proportion of strange quarks, you could create something that's, well, stronger, more resilient, like finding a secret alloy that's tougher than steel, but made from the very fabric of existence. This stability hinges on a delicate dance of forces, a concept called baryon number and equilibrium. In the incredibly dense environments found within neutron stars, for instance, or perhaps in the immediate aftermath of the Big Bang, matter is squeezed to unimaginable pressures. Under these extreme conditions, the thermodynamic equilibrium might actually favor the formation of these stable strangelets. It's like a crowded room where people naturally clump together in the most comfortable, least energetic arrangements. In this cosmic pressure cooker, the strange quarks might find their most stable home, binding together with their up and down brethren, creating these exotic, robust little packets of matter. The theoretical foundation for this astonishing idea comes from the pioneering work of physicists like Bodmer and Wenzel. They were the ones who first dared to whisper this radical thought into the scientific ether, suggesting that perhaps our understanding of matter was incomplete, that there was a hidden, stranger form waiting to be discovered. It's a testament to human curiosity, isn't it? To look at the known, the familiar, and ask, what if there's something else? Imagine a pile of different colored Lego bricks. Normally you'd build structures with just red and blue. They're the familiar colors, the ones you always reach for. But what if a mix of red, blue, and green bricks, when combined in just the right ratio, formed a structure that was incredibly strong and self-sustaining? A structure that, once formed, would simply continue to exist, perhaps even absorbing other bricks to grow? That's a little like the strangelet hypothesis. It's about finding that unexpected combination, that unique ratio of fundamental particles that unlocks a new level of stability and persistence. If strangelets are potentially stable, if they can exist in this more robust form, then a delightful, and perhaps slightly unsettling, question naturally arises: where might we expect to find them, or how might they form in the vast, mysterious tapestry of the universe? It's a question that sends our minds drifting, like dandelion seeds on a gentle breeze, towards the most extreme corners of the cosmos. The theoretical possibility of stability leads us to ponder the cosmic nurseries where such exotic matter could be born. Imagine, if you will, the universe as a vast, simmering cauldron, and within its deepest, most intense pockets, the very fabric of reality is pushed to its absolute limits. Our first stop on this journey into the extreme is the neutron star. Think of it as the ghost of a star that lived a truly colossal life, burning bright and fast, and then in its final, spectacular act, collapsing inwards upon itself. It's the ultimate cosmic immolation, leaving behind a core so dense, so unbelievably compact, that a single teaspoon of it would weigh more than all the mountains on Earth combined. It's a celestial diamond, but forged not by gentle pressure over owens, but by the catastrophic implosion of a stellar titan. Inside these neutron stars, the pressures are simply unfathomable. They are the universe's ultimate pressure cookers, where the ingredients of matter are squeezed so tightly that their usual forms can no longer hold. Protons and electrons, the familiar building blocks of atoms, are forced together under such immense gravitational embrace that they can no longer exist as separate entities. They merge, they fuse, they become neutrons. And in this incredible density, this crushing embrace, we hypothesize that something even stranger might occur. It's within the very heart of these neutron stars, in their impossibly compressed cores, that the conditions could be just right for the formation of strange matter. Here, the neutrons themselves might be further broken down. Imagine the neutrons, those sturdy neutral particles, being squeezed so hard that even they can't maintain their composure. They might shatter, releasing their constituent quarks, the up and down quarks that make them up, and allowing for the possibility of strange quarks to join the party. If strange quarks, with their peculiar, heavier nature, find themselves in this ultra-dense environment, they might bind with the existing up and down quarks, forming a stable, or perhaps even more stable, form of matter. This hypothetical core, a nucleus of strange quarks and nucleons, is what we call strangelet, or, more broadly, strange matter. It's like a new kind of fundamental substance, born from the ultimate cosmic squeeze. It's as if the universe, in its most extreme moments, is experimenting with new recipes for reality itself. But these stellar hearts aren't the only places where such dramatic transformations might occur. Consider the violent dance of the cosmos, the breathtaking ballad of celestial collisions. When two neutron stars, those incredibly dense stellar corpses, spiral towards each other and finally merge, the energies released are simply mind-boggling. These are cataclysmic events, the universe's most violent embraces, and in the maelstrom of such a merger, the extreme pressures and temperatures could very well create and then scatter these strangelets across the vastness of space. Imagine them flung out like cosmic shrapnel, tiny packets of exotic matter hurtling through the void. And let's not forget the very beginning. The early universe, in those fleeting, incandescent moments after the Big Bang, was a place of unimaginable density and energy. It was a primordial soup, a crucible where the fundamental forces were still settling, and the very nature of matter was being sculpted. It's entirely plausible that during this brief, chaotic infancy, the conditions were ripe for the formation of strangelets, perhaps even in larger quantities than we might find today. They could have been born in that initial, blinding flash, remnants of a universe still finding its feet. So, we have these stellar ovens, these cosmic pressure cookers, and the initial fiery burst of creation as potential birthplaces for strange matter. Neutron stars are like cosmic pressure cookers, where the ingredients of matter are squeezed so tightly that their usual forms can no longer hold. It's in these extreme ovens that strange new compounds might bake. If strangelets are indeed forming in these extreme environments, how might we detect their presence, or what evidence could they leave behind? It's a question that beckons us to look closer, to listen to the whispers of the universe, and to ponder the hidden forms matter might take. The universe is vast, but it often leaves subtle breadcrumbs for those who know where to look. How do we hunt for the invisible? It's a question that hums in the quiet spaces between the stars, a whisper we try to catch with our most sophisticated ears. We're talking, of course, about the tantalizing possibility of strange matter, and how we might actually find it out there in the cosmic ocean. Imagine, if you will, the most violent, the most spectacular dances in the cosmos. We're talking about the mergers of neutron stars. These are the collapsed hearts of giant suns, incredibly dense, spinning at dizzying speeds, packed so tightly that a teaspoon of their material would weigh as much as a mountain. When two of these behemoths spiral into each other, it's an event of unimaginable energy. It's a cosmic collision that rips through spacetime itself, sending out ripples we can now detect with instruments like LIGO and Virgo. These aren't just gravitational waves, though. These events also paint the sky with light, with gamma rays and X-rays a dazzling, fleeting signature. By observing both the gravitational whispers and the electromagnetic shouts, scientists can begin to piece together clues about what's happening inside these infernos. They can, in a way, taste the very fabric of these collapsed stars, looking for hints of something different. And that's where our search for strange matter truly begins. We're looking for anomalies, for deviations from the expected. Think about it. If a neutron star were to contain a core of strange matter, a sea of up, down, and strange quarks, it might behave just a little bit differently than a star made purely of neutrons. Perhaps its mass-radius relationship would be a touch off. Maybe its cooling rate, the way it sheds its residual heat after formation, would be subtly altered. These are those tiny cracks in the expected narrative, the faint irregularities that might point to a deeper, stranger truth within. It's like noticing a single perfectly smooth, black pebble on a beach covered in white, rough stones. It stands out, not because it's loud, but because it's uniquely quiet in its difference. Beyond the direct observation of neutron stars, there's another avenue, a more ethereal one. We're talking about cosmic rays. These are high-energy particles that stream across the galaxy, carrying with them the echoes of distant, violent events. If strange matter exists, and if it were to be ejected from some cataclysmic encounter, perhaps a neutron star merger or a supernova, it might travel through space as a strangelet. These hypothetical particles, these tiny nuggets of strange matter, could be zipping through the universe right now. And we have instruments, incredibly sensitive particle detectors on Earth and in orbit, designed to catch these fleeting visitors. They're like cosmic fishermen, casting nets of exquisite sensitivity into the vast ocean of particles, hoping to snag something truly extraordinary. But here's the rub, the grand challenge of this cosmic treasure hunt. Detecting strangelets is like trying to find a specific, rare type of seashell on an entire beach. You need incredibly sensitive tools and a keen eye for the subtle differences that set it apart. Imagine sifting through billions upon billions of ordinary grains of sand, each one a common particle, looking for that one unique shell with its peculiar pattern, its unusual weight. The universe throws so much at us, so many energetic particles, so many exotic phenomena, that isolating a signal that might only come from a strangelet is incredibly difficult. It requires not just sensitive instruments, but also a deep understanding of all the other things those instruments might see. We have to be absolutely sure we're not mistaking a particularly energetic proton, or a fragment from a known astrophysical process, for the very thing we're seeking. It's a dance of elimination, a process of ruling out the ordinary to reveal the extraordinary. And this brings us to a rather profound, and perhaps a little unsettling thought. What if a strangelet were to reach Earth? The theoretical implications for our planet are profound, and perhaps a little unsettling. If a stable strangelet, a tiny speck of this exotic matter, were to encounter ordinary matter, the theories suggest it could, in a rather dramatic fashion, convert that ordinary matter into more strange matter. It's a kind of cosmic contagion, a chain reaction that could, in theory, transform everything it touches. Of course, this is highly speculative, a theoretical endpoint that many physicists believe is unlikely to happen with any significant speed or scale, but the sheer possibility hangs in the air, a silent question mark in our understanding of the universe. It's the thought of a single, almost imperceptible entity holding the potential for such vast, transformative power that truly sparks our curiosity and, perhaps, a shiver of awe. Now, here's where the concept of strange matter moves from the cosmic to the potentially terrestrial, with a truly startling hypothesis. It's a thought experiment that tickles the edges of our imagination, a whisper of a possibility that's both profoundly unsettling and, in its own way, incredibly fascinating. We're talking about the strangelet conversion hypothesis. Imagine, if you will, a tiny, impossibly dense speck of strange matter, a strangelet, somehow finding its way into our everyday world. The theory suggests that if this strangelet possesses a sufficient amount of mass and density, and if it were to collide with ordinary matter, it might not just bounce off. Instead, it could initiate a truly remarkable process, converting that ordinary matter into more strange matter. Think of it like a ripple spreading across a still pond, but instead of water, it's the very fabric of atomic nuclei. When a strangelet encounters a nucleus of ordinary matter, like the carbon in your hand or the oxygen you're breathing, the immense pressure and unique quantum state within the strangelet could, theoretically, force the quarks within the normal nucleus to reconfigure themselves. The up and down quarks that make up protons and neutrons might be nudged, persuaded, or even compelled to rearrange into the more stable, lower energy configuration that includes strange quarks. This isn't just a single conversion, it's the potential for F-chain reaction. If one nucleus is converted, it becomes a new strangelet, albeit perhaps a smaller one. This new strangelet then has the capacity to collide with its neighbor, and so on. It's like a domino effect, but instead of toppling, each domino transforms into a denser, stranger version of itself. This is the concept of a strangelet bomb, a runaway process where ordinary matter is steadily, inexorably transformed into this exotic, super dense form. It's a thought that conjures images of a silent, invisible transformation, a slow, motion cosmic alchemy happening at the most fundamental level of reality. Now, for this dramatic conversion to even begin, there's a theoretical hurdle, the critical size. Scientists hypothesize that a strangelet needs to reach a certain minimum size, a threshold of mass and density, to overcome the inherent stability of ordinary atomic nuclei and initiate this conversion. Below that size, it might be like a tiny pebble dropped into a vast ocean. It simply gets absorbed or deflected without causing any significant change. But above that threshold, well, that's where the more dramatic scenarios begin to play out. This leads us to the popular, and admittedly highly speculative, concern that strangelets from cosmic sources, perhaps born in the violent heart of a neutron star collision or the energetic aftermath of a supernova, could pose an existential threat to Earth. The idea is that if such a strangelet, of sufficient size and energy, were to pass through our planet, it could potentially convert our entire world, atom by atom, into strange matter. It's a doomsday scenario that captures the imagination, a stark reminder of the vast and sometimes terrifying forces at play in the universe. To help us grasp this rather mind-bending concept, let's try an analogy. Imagine a single sugar crystal dropped into a supersaturated solution of sugar. What happens? It acts as a seed, a perfect nucleation point, causing rapid crystallization. The dissolved sugar molecules are drawn to that crystal, arranging themselves into the same ordered structure, and the solution transforms into a solid mass. A strangelet, in this theoretical scenario, might act similarly, but on a nuclear scale. It's not just a seed for crystallization, it's a seed for a fundamental change in the very nature of matter, converting normal matter into its own dense, strange form. It's a potent image, isn't it? A tiny speck holding the potential to rewrite the material composition of everything around it. Given these dramatic theoretical possibilities, the mind naturally drifts to a crucial question: what is the scientific consensus on the actual likelihood of such a conversion occurring? It's a question that weighs heavily, especially when we consider the implications. And that, dear friends, is where our journey into the strangelet conversion hypothesis takes us. What are your thoughts on the potential dangers and scientific curiosities surrounding this truly mind-bending idea? The idea of cosmic conversion, of this strange, alien matter whispering its way through the cosmos and potentially rewriting our reality, it's undeniably captivating, isn't it? It tugs at that primal part of us that wonders about the truly unforeseeable. But then the scientist in me, or perhaps just the cautious observer, whispers back, how does this grand, almost mythical, concept actually stand up to rigorous scientific examination? And more importantly, what about the practicalities of risk? Let's gently unfurl this question, starting with the sheer, mind-boggling ways probability of encounter. Imagine the universe not as a vast, empty void, but as an ocean of unimaginable scale, teeming with countless currents and tides. Our Earth, our little blue marble, is but a single, tiny droplet in that boundless expanse. And a strangelet, a rogue wanderer from some exotic corner of existence, would be an even tinier speck, a cosmic mote of dust, adrift in that immensity. The sheer distances involved, the infinitesimal chance of a direct collision, of a strangelet finding its way to our doorstep. It's astronomically low. We're talking about probabilities so small they're almost as abstract as the concept itself. Now, consider what we're already constantly exposed to. Our planet is perpetually bathed in a relentless deluge of cosmic rays. These are not gentle whispers, they are high-energy particles, protons and atomic nuclei, zipping through space at near light speed, a constant energetic bombardment. They slam into our atmosphere, into our very ground with incredible force. And yet, normal matter, the stuff of stars, of you and me, of this very microphone, it's remarkably resilient. It absorbs this onslaught, it deflects it, it continues to be. When we compare the potential hypothetical impact of a single, slow-moving strangelet to the ceaseless, violent torrent of cosmic rays, the threat of the latter, while also incredibly unlikely to cause catastrophic conversion, seems a far more tangible, albeit still minuscule, concern. Our everyday reality is already a testament to the robust nature of ordinary matter. This brings us to the echoes of past concerns, particularly around the Large Hadron Collider, and the anxieties that swirled like dark clouds when it first flickered to life. There were whispers, fears, that such powerful machines, designed to probe the fundamental building blocks of reality, might inadvertently create something dangerous. Something that could, perhaps, trigger a runaway conversion. But as the scientific community delved deeper, as they ran simulations, as they understood the energies and the conditions involved, those fears were systematically reassessed and, for the most part, allayed. The energies produced in these accelerators, while immense, are still far from the conditions that theoretical models suggest would be necessary for stable strangelet formation and subsequent conversion. It's like trying to start a wildfire with a single spark in a rainstorm. And perhaps the most compelling argument, the silent witness to all this speculation, is simply this lack of observed catastrophes. If strange matter possessed this inherent, unstoppable drive to convert everything it touched, if even a tiny, rogue strangelet could initiate such a domino effect, wouldn't we have seen some evidence by now? Wouldn't there be cosmic anomalies, celestial bodies mysteriously consumed, or even subtle terrestrial shifts that pointed to such a phenomenon? The universe is ancient, vast, and full of wonders, but it's also remarkably orderly in its grand sweep. We haven't observed any cosmic event, any terrestrial anomaly, that whispers of a strangelet conversion as its cause. It's a bit like worrying about a single dandelion seed that has somehow managed to travel all the way from another galaxy, landing in your meticulously tended garden, and somehow, inexplicably, causing your entire prize-winning rose bush to transform into a field of dandelions. The sheer scale of the universe, the nature of matter, the established laws that govern them, they have their own, incredibly robust ways of dealing with such minuscule, improbable intrusions. It's a beautiful image, though, isn't it? A cosmic dandelion seed. So, if the immediate existential threat, the dramatic universe-ending scenario, appears to be vanishingly small, then what other, perhaps more subtle, ways might strange matter, or the very idea of it, influence our understanding of the universe? If it's not a cosmic boogeyman waiting to consume us, what else can it teach us? What deeper questions does it beckon us to explore? Beyond dramatic conversion scenarios, could strange matter play a more enigmatic role, perhaps in one of the universe's greatest mysteries? It's a question that whispers through the cosmic silence, a tantalizing possibility that tugs at the edges of our understanding. We've spent a good deal of time exploring the peculiar nature of strange matter, this theoretical substance born from the deep, dense heart of neutron stars. But what if its story doesn't end there? What if, instead of vanishing in a flash of energy, it's out there everywhere, woven into the very fabric of the cosmos, unseen and yet profoundly influential? This brings us to one of the most persistent and profound enigmas in modern astrophysics, dark matter. Imagine looking up at the night sky, at the swirling galaxies and the distant nebulae, and knowing that all of that luminous, sparkling beauty, all the stars, planets, gas clouds, the very light that reaches our eyes accounts for only a tiny fraction, perhaps just 5%, of the total stuff in the universe. The rest, a staggering 95%, is something else entirely. Something dark. Something we can't see, can't touch, and can barely even comprehend. Dark matter isn't just a placeholder for our ignorance. It's a necessity born from observation. We see its gravitational fingerprints everywhere. Galaxies spin far too fast to hold themselves together with just the visible matter they contain. Without the extra gravitational glue provided by this invisible substance, they would simply fly apart, like a carousel spinning so wildly that its passengers are flung into the void. Galaxy clusters, vast cosmic cities, are also held together by a gravitational force far stronger than what their luminous inhabitants can provide. It's as if the universe is wearing a cloak of invisibility, a vast unseen scaffolding that shapes the grand structures we do observe. So, what do we all know, or rather, what do we infer, about this elusive dark matter? Well, we know it interacts gravitationally. That's how we detect its presence. It pulls and it tugs, bending light, influencing orbits, dictating the cosmic dance. But it doesn't interact with light in any other way. It's non-luminous, meaning it doesn't emit, absorb, or reflect light. It's as if it's made of pure shadow, a silent observer that leaves its mark only through gravity's gentle caress. And, as we've said, it's abundant, making up the lion's share of the universe's mass. Now enter our strangelets. These hypothetical lumps of strange quark matter, if stable, could possess precisely the properties we're looking for in dark matter. They would be massive, interacting only through gravity, and if they formed in the early universe, or perhaps from the remnants of neutron star collisions, they could be scattered throughout the cosmos. Imagine tiny, incredibly dense specks, each a miniature universe of quarks, drifting silently through the vast emptiness. They wouldn't shine, they wouldn't reflect, but their collective gravitational pull could indeed be the unseen engine driving galactic rotation and holding clusters together. It's a compelling thought, isn't it? That the very substance we've been searching for, this cosmic phantom, could be a byproduct of extreme stellar physics, a relic from the universe's fiery birth. However, as is often the case in the grand theater of science, this elegant hypothesis runs into some rather stubborn challenges. The universe, it turns out, is a rather stringent critic, and it doesn't always play by our neat theoretical rules. For strangelets to be a significant component of dark matter, they would need to have survived the cosmic journey without causing too much trouble. For instance, if strangelets were common enough to be dark matter, and if they were able to convert ordinary matter they encountered into strange matter, a process known as strange matter ignition, we would expect to see dramatic and easily detectable astrophysical events. Think of it like a cosmic domino effect, where one strangelet could potentially trigger a chain reaction, converting entire stars or even planets into strange matter. We simply haven't observed events of that magnitude with the frequency that would be expected if strangelets were the dominant form of dark matter. There are also observational constraints from things like the cosmic microwave background radiation, the faint afterglow of the Big Bang, and the abundance of light elements formed in the early universe. These observations paint a picture that doesn't always align perfectly with the presence of a significant population of stable strangelets. The universe, it seems, has a way of checking our homework, pointing out where our beautiful theories might have a few smudged numbers. Imagine trying to explain why your car is moving without seeing the engine. Dark matter is that unseen engine. Some theorize strangelets could be the gears within it, but the analogy doesn't perfectly fit all the observed behaviors. The gears might be grinding in a way that suggests a different kind of engine altogether. While strangelets might not be the sole answer to dark matter, what other exotic forms of matter are scientists considering? The search continues, a testament to our insatiable curiosity, our deep-seated need to understand the unseen forces that shape our reality. The universe holds its secrets close, but with every new observation, every refined theory, we inch closer to deciphering its hidden language. The universe is a canvas for imagination, and physics continues to paint with possibilities far beyond our current grasp. We've been dancing with the idea of strangelets, these hypothetical little nuggets of strange quark matter. But the universe, in its infinite, playful wisdom, doesn't stop at just one peculiar creation. Imagine, if you will, that deconfined quark matter itself in a broader sense, could be the building block for something even grander, something that hums with its own cosmic gravity. We're talking about the possibility of quark stars. Not stars like our familiar sun, a fiery ball of plasma held together by nuclear fusion, but something far more dense, far more alien. Picture a star where the very protons and neutrons we know have dissolved, their constituent quarks up, down, and strange unbound, swirling freely in a dense, exotic soup. It's like taking a perfectly formed, intricate clockwork and melting it down, letting the individual gears and springs exist in their own chaotic, yet perhaps ordered dance. And within this swirling sea of quarks, there's another fascinating theoretical state that physicists ponder: color superconductivity. Now, this isn't about electrical currents flowing through wires, but about the fundamental forces that bind quarks together. Think of the strong nuclear force, which is mediated by particles called gluons. These gluons carry a property called color charge, which is a bit like electric charge, but much more complex. In this theoretical state, quarks might pair up, much like electrons do in conventional superconductors, forming Cooper pairs. But instead of flowing without electrical resistance, these quark pairs might flow without resistance to the strong nuclear force. It's a concept so abstract, it's like trying to describe the taste of a color you've never seen. Imagine a liquid that flows not just smoothly, but with an inherent unbreakable unity, where every drop is perfectly synchronized with every other drop, all bound by an invisible, potent force. Beyond these, the theoretical landscape is dotted with other intriguing possibilities. We're talking about hypothetical particles and composites that could arise under the most extreme pressures and densities imaginable. Perhaps combinations of quarks and anti-quarks, forming fleeting, exotic structures that defy our everyday intuition. It's like finding a hidden chamber in a vast, ancient library, filled with scrolls written in languages we haven't yet deciphered, hinting at stories of matter that exists in forms we can only dream of. These aren't just wild guesses. They are the logical extensions of our current understanding, the whispers of what might be lurking at the very edges of existence. It's crucial to remember that these are the bleeding edge of theoretical physics. They are ideas, elegant equations, and thought experiments that push the boundaries of what we can observe and measure. The universe is a vast, enigmatic playground, and these exotic matter forms are like its most peculiar, most elusive toys, still being discovered and understood. If strangelets are one type of unusual gemstone, then these other exotic matter forms are like different cuts or compositions of rare minerals, each with its own unique theoretical properties. Some might be as hard as diamond, others as fluid as mercury, all existing under conditions so extreme they're almost impossible to replicate here on our gentle, familiar Earth. How do these theoretical constructs, like strangelets and other exotic matter, relate to the fundamental forces that govern our universe? That's the next, magnificent question we'll gently explore. To understand strange matter, we must revisit the invisible threads that weave the fabric of reality, the fundamental forces. Think of them as the universe's silent orchestra, each playing a crucial, yet often unseen, part in the grand symphony of existence. We've touched upon them before, but now, as we peer into the heart of this peculiar hypothetical substance, their roles become even more profound, like rediscovering ancient melodies that define our very being. First, there's the strong nuclear force. This is the ultimate cosmic hug, the tenacious embrace that binds quarks together, forming protons and neutrons. It's a force so powerful, so incredibly potent, that it's like trying to pull apart two best friends who are absolutely determined to stay together. Within a strangelet, this force would be the undisputed king, the dominant conductor, holding those strange quarks in an incredibly dense, tightly packed arrangement. It's the reason why, even under immense pressure, these exotic particles might maintain their peculiar form, a testament to the sheer tenacity of this fundamental interaction. Then we have the electromagnetic force. This is the force of attraction and repulsion, the dance of positive and negative charges. If a strangelet carries a net electrical charge, this force would paint a whole new set of interactions. Imagine a tiny, impossibly dense sphere, humming with unseen electrical energy. It would respond to magnetic fields, perhaps even generating its own, like a miniature, cosmic dynamo. It's the force that allows light to travel, that holds atoms together in molecules. And here, it would be the subtle, yet significant, brushstroke on the canvas of strange matter's behavior, dictating how it might mingle or repel with other charged particles or fields in the vast cosmic ocean. Next, the weak nuclear force. This is the quiet transformer, the subtle alchemist of the subatomic world. It's responsible for certain types of particle decay, for the slow, patient transformation of one particle into another. While the strong force is the immediate forceful binder, the weak force operates on much longer timescales, a gentle whisper of change. It's the force that might, over eons, allow a strangelet to subtly shift, to perhaps decay into more familiar forms, or to interact in ways we can only begin to imagine. It's the slow erosion of a mountain, the gradual aging of a star, a reminder that even the most exotic matter is subject to the universe's patient, unfolding narrative. And finally, we can't forget gravity. Gravity, the grand architect of cosmic structures, the relentless sculptor of the universe. It's gravity that compresses gas clouds into stars, that crushes stars into dense remnants like neutron stars. It's gravity that provides the immense pressure, the crushing weight that could, in theory, push matter to such extreme densities that it might even condense into strange matter. Imagine the universe itself like a colossal hand, squeezing and squeezing, until the very building blocks of reality are forced into entirely new, unexpected configurations. Gravity is the ultimate enabler, setting the stage for the emergence of these exotic states. So, you see, the four fundamental forces are like the invisible hands shaping matter. The strong force is the tight grip holding quarks together, gravity is the immense pressure squeezing them, and the weak and electromagnetic forces are the subtler influences on their behavior, dictating their interactions and potential transformations. They are the unseen architects, the silent sculptors, working in concert to create the incredible diversity of the cosmos. With this understanding of forces, let's consider the philosophical implications. What does the existence of such matter tell us about the nature of reality itself? If matter can exist in these incredibly dense, perhaps even stable, exotic forms, what does that suggest about the boundaries of what's possible? It's like discovering that the colors you thought existed are just a small part of a much larger, unseen spectrum, waiting to be perceived. It makes you wonder about the universe's boundless creativity, its capacity for surprise, and the profound interconnectedness of all things, from the smallest quark to the grandest galaxy, all governed by these fundamental invisible laws. As we delve into the truly exotic, the boundaries between physics and philosophy begin to blur, inviting deeper contemplation. We've been exploring these strange, hypothetical forms of matter, and it really makes you pause and ask, what is matter, anyway? Our everyday experience, the world we touch and taste and see, is built on familiar building blocks. We think of matter as having mass, taking up space, being composed of atoms with protons, neutrons, and electrons. It's solid, it's liquid, it's gas. These are our anchors. But what happens when we encounter something like strange matter, a theoretical substance forged from hyperons, particles we rarely encounter in our terrestrial lives? Does it still qualify as matter? Perhaps matter isn't defined solely by its ingredients, those familiar protons and electrons, but by its properties, its interactions, its sheer existence as a fundamental constituent of the cosmos. Or maybe it's about its potential, its capacity to exist, to form, to shape the universe in ways we haven't even begun to imagine. It's like trying to define life. Is it the DNA, the ability to reproduce, or that spark of awareness that flickers within? This theoretical existence of strange matter, tucked away in the hearts of neutron stars, or perhaps even scattered across the cosmos, paints a picture of a universe that is so much richer and more varied than our current observations might readily reveal. We tend to look at the night sky, at the familiar glow of stars and the silent dance of galaxies, and feel like we have a grasp on the cosmic tapestry. But imagine if the universe is like a vast, uncharted library, and we've only managed to read a single, well-worn volume. Strange matter, in its very possibility, suggests there are entire sections of that library filled with stories written in a language we're only just beginning to decipher, stories about entirely different kinds of existence. It hints at a cosmic diversity that stretches far beyond our current, perhaps limited understanding. And this, in turn, forces us to confront the profound limits of our own human perception and cognition. We are, after all, creatures of this particular planet, shaped by billions of years of evolution on Earth. Our senses, our brains, our very ways of thinking are finely tuned to this reality, to the gentle pull of gravity, the spectrum of visible light, the comforting hum of our atmosphere. But what if the universe operates on principles that lie just beyond the reach of our senses, like a melody played just outside the range of our hearing? What if the universe is humming with frequencies, with forms of energy, with states of matter that our current biological equipment simply isn't equipped to detect? It's a humbling thought, isn't it? It suggests that to truly understand the cosmos, we might need to find ways to transcend these inherent limitations, to expand our awareness, to develop new senses, or new ways of interpreting the data the universe is constantly sending us. This leads us to a beautiful philosophical idea, the principle of plenitude. It's this notion that if something is possible, if it can exist without logical contradiction, then it might exist somewhere in the vastness of the cosmos. Think of it like this. If we only ever saw water as ice, solid and unyielding, we might struggle to conceive of liquid water, flowing and adaptable, or even steam, ethereal and invisible. Strange matter is like discovering entirely new states of water that operate under fundamentally different rules, expanding our definition of what water can be, and by extension, what matter can be. If the universe is so full of potential, so brimming with possibilities, what does this mean for our place within it and our understanding of consciousness? Does consciousness itself have different forms, different densities, different frequencies, waiting to be discovered in the cosmic ocean? It's a question that whispers at the edge of our understanding, inviting us further into the mystery. From the dense heart of exotic matter, our gaze can now turn inwards, to the equally mysterious realm of consciousness. We've journeyed through the tangible, the strange, the almost unimaginable densities of things like strange matter, but now, let's gently pivot. Let's turn our attention from those outer edges of the universe's composition to the equally profound, perhaps even more baffling, landscape within ourselves. It's a shift from the palpable to the perceived, from the stuff of stars to the very essence of being. And here, we bump into one of philosophy's most persistent, most ticklish questions: how does mere physical stuff, the atoms and molecules that make up our brains, somehow conjure the rich tapestry of subjective experiency? How does the cold, unfeeling dance of neurons blossom into the warmth of love, the sting of regret, the quiet hum of contentment? It's like asking how a pile of clay, no matter how intricately sculpted, can suddenly feel the sun on its surface, or taste the rain. This is the chasm between the physical and the phenomenal, the hard problem of consciousness, and it's a mystery that echoes in the very structure of existence. This leads us to a rather daring thought, doesn't it? What if consciousness isn't just something that happens to complex brains, like a particularly elaborate byproduct of electrical signals? What if, instead, consciousness is something more fundamental? Imagine it not as a delicate bloom that sprouts only on the fertile soil of a highly evolved brain, but as a universal field, a subtle, pervasive quality woven into the very fabric of reality itself. Perhaps it's a property as intrinsic as mass or charge, present, albeit in vastly different forms, throughout the cosmos. And if we consider this idea, then the concept of vibrational frequencies takes on a whole new, shimmering dimension. We've spoken of how exotic matter might possess unique vibrational signatures, how its very existence implies a different way of resonating with the universe. If consciousness is also a form of vibration, a way of processing information at a fundamental level, then perhaps different forms of matter, including these hypothetical exotic materials, might interact with consciousness in ways we can only begin to imagine. Could strange matter, with its unique quantum properties, be a conduit for particular kinds of conscious resonance? Could it tune into frequencies of awareness that our ordinary matter simply cannot? It's a thought that dances tantalizingly close to the observer effect in quantum physics, isn't it? That simple act of looking, of measuring, can actually change the behavior of a quantum system. It's as if the universe at its most fundamental level is aware that it's being observed, This isn't to say that a rock possesses sentience, of course, but it hints at a far deeper interplay, a subtle, perhaps even intimate, connection between the act of conscious observation and the very unfolding of physical reality. It's like the universe is a shy performer, and our attention, our conscious gazing, subtly alters the dance. Imagine the universe as a vast, cosmic symphony. Ordinary matter, the stuff of our everyday lives, plays certain familiar, resonant notes, the steady rhythm of gravity, the gentle hum of electromagnetism. But exotic matter, with its strange densities and unusual properties, might play entirely different, perhaps even as inaudible frequencies to our current understanding. It might be the deep bass notes that we can feel more than hear, or the ethereal harmonics that shimmer just beyond our normal perception. And consciousness. Consciousness is like the listener, the one who perceives and interprets these myriad vibrations. It's the ear that catches the melody, the heart that feels the rhythm, the mind that weaves it all into a coherent experience. And if consciousness is so deeply intertwined with the fabric of reality, if it's not just an observer, but a participant in this cosmic symphony, then the question becomes even more intriguing. Could certain forms of matter, like strange matter, with its potentially unique vibrational signatures, interact with consciousness in ways we haven't yet conceived? Could they be antennae for different conscious experiences? Could they offer new pathways, new frequencies, for awareness to explore? It's a thought that opens up a universe of possibilities, a gentle nudge towards understanding that the stuff of existence and the experience of being might be far more intimately connected than we ever dared to dream. Let's explore this intriguing possibility. Could exotic matter, in its very nature, possess qualities that resonate with consciousness? It's a thought that tickles the edges of our understanding, isn't it? We're so accustomed to thinking about matter in terms of its heft, its charge, the way it pushes and pulls against our familiar senses. But what if there are other ways to describe it, ways that lie beyond the simple metrics of mass and electrical charge? Imagine matter not just as a collection of particles, but as a symphony of inherent vibrational states. Think of it like a finely tuned instrument, each atom, each subatomic particle, humming its own unique tune. And perhaps, just perhaps, some of these tunes are so exquisitely complex, so deeply interwoven, that they carry information. Not just raw data, but a kind of encoded essence, a whisper of something more profound. We talk about the frequency of matter, and it's a beautiful, almost poetic notion. But what if this isn't just a metaphor? What if different states of matter, especially those we call exotic, genuinely possess unique energetic frequencies, like distinct signatures in the grand cosmic song? Imagine the dense heart of a neutron star, or the shadowy presence of dark matter. These aren't your everyday garden variety substances. They exist in conditions so extreme, so far removed from our everyday experience, that their very fundamental vibrations might be utterly alien to us. They might be singing songs we can't yet hear, with instruments we haven't yet invented. And this leads us to a fascinating speculation, the potential for subtle interaction. If these exotic forms of matter are indeed vibrating at these incredibly unique frequencies, could they interact with the subtle energy fields that we believe underpin consciousness? Think of it like this: our consciousness, our very awareness, might also have its own intricate energetic patterns, its own unique frequency. And if exotic matter possesses a particularly potent or unusual resonance, it's conceivable that there could be a form of interaction, a delicate dance, that's currently beyond our ability to detect. It's like trying to feel the warmth of the sun on your skin when you're deep underground. The sun is there, its energy is radiating, but the barrier is too great for our current senses. This is where the very heart of our channel, the idea of conscious frequency, finds its echo. Perhaps the universe's most profound secrets, the deepest mysteries of existence, are not hidden in grand, explosive events, but rather in the subtle, almost imperceptible frequencies of its most unusual constituents. It's a thought that makes you pause, isn't it? That the very fabric of reality, in its most bizarre and extreme manifestations, might hold the keys to understanding our own inner universe. Think of a crystal tuning fork. It vibrates at a specific, pure frequency when struck. It's a clean, unwavering tone that can resonate with other objects, causing them to vibrate in sympathy. perhaps exotic forms of matter, due to their unique quantum states, possess their own fundamental resonances that could, in theory, interact with subtler universal patterns. Imagine these exotic materials as cosmic tuning forks, each emitting a distinct, perhaps incredibly complex, vibrational signature. And if consciousness itself is a form of vibration, then it's not so far-fetched to imagine a sympathetic resonance, a subtle coupling between these cosmic vibrations and our own inner experience. It's a beautiful, almost musical idea. If these are speculative ideas, what are the more concrete, observable phenomena that scientists are still trying to explain with our current understanding of matter? It's a question that naturally arises, isn't it? We've touched upon the edges of the unknown, and it begs the question: what are the solid groundings, the observable anomalies, that hint at these deeper possibilities? What are the cosmic puzzles that our current textbooks simply can't quite solve, the whispers of a reality that might be far stranger, and perhaps far more interconnected, than we've dared to imagine? It's these questions, these persistent curiosities, that keep us exploring, keep us wondering, and keep us tuning into the subtle frequencies of existence. The universe is a grand tapestry, and some threads remain stubbornly out of place, inviting new explanations. It's like finding a perfectly smooth, perfectly spherical stone on a beach filled with rough, irregular ones. It makes you wonder about its origin, and if it came from a different, more orderly place. And in the vast cosmic ocean, we're finding quite a few of those smooth, round stones, aren't we? Take, for instance, these whispers from the void we call fast radio bursts, or FRBs. Imagine for a fleeting moment a colossal cosmic lighthouse, flashing with unimaginable power, sending a brief, intense burst of radio waves across billions of light years. These aren't gentle hums, they are sudden, sharp exclamations from the deep. For years, they were just that, unexplained. Where did they come from? What colossal event could unleash such focused energy? We've heard them repeat, some of them, like a cosmic echo, but their origin remains a tantalizing riddle. Some theories, the more adventurous ones, even whisper about exotic matter, about things we haven't quite grasped yet, being the source of these celestial shouts. And then there are the anomalous gamma-ray bursts. These are the universe's most violent, most luminous explosions, the cosmic equivalent of a supernova dialed up to 11, then some. But within the patterns of some of these incredibly energetic events, astronomers have noticed oddities. Subtle deviations, moments that don't quite fit the established astrophysical models. It's like watching a symphony where one instrument, for just a beat, plays a note that's entirely unexpected, yet somehow it doesn't shatter the harmony. These anomalies, these whispers of deviation, could be clues pointing towards astrophysical processes we haven't even dreamed of yet, or perhaps, as we've been exploring, the subtle fingerprints of matter that behaves in ways we're just beginning to understand. It's a familiar dance for science, isn't it? We've had these moments before. Think back to the Pioneer anomaly. For decades, the Pioneer spacecraft, those brave little Voyagers, seemed to be experiencing a tiny, inexplicable tug, a subtle deviation from their predicted trajectory. It was a cosmic nudge that defied easy explanation, a tiny cosmic itch that science couldn't quite scratch with the tools it had. And it was through grappling with that very anomaly, through persistent observation and a willingness to consider the as unexplained, that we eventually found new physics, a deeper understanding of gravity and the subtle forces at play in our universe. These unexplained phenomena, these cosmic riddles, they aren't roadblocks, they are invitations. Invitations to expand our understanding, to push the boundaries of our knowledge. And that's precisely what FRBs and anomalous GRBs are doing now. They are the cosmic equivalent of that smooth, round stone demanding a new explanation, a new chapter in our understanding of the universe's fundamental building blocks. They are nudging us, gently but persistently, towards the idea that the Standard Model, our current best description of fundamental particles and forces, might not be the complete story. They are the breadcrumbs leading us into the wilderness of physics beyond the Standard Model, a wilderness where exotic matter with properties we can only speculate about, might very well hold the keys to these cosmic mysteries. It's in these unexplained signals, these cosmic hiccups, that we might find the first tangible evidence of entirely new forms of matter, or entirely new forces shaping the cosmos in ways we're only just beginning to perceive. As we move towards concluding our exploration of strange matter, what are the ultimate questions it leaves us with about the universe's composition and evolution? These persistent enigmas, these cosmic whispers of the unusual, they beckon us to ponder. Are we truly seeing the universe as it is, or are we only glimpsing a fraction of its true, perhaps stranger nature? Are these phenomena merely the result of extreme astrophysical conditions, or are they the subtle, yet profound, signatures of matter that exist beyond our current comprehension? Matter that might have played a far more significant role in shaping the cosmos than we've ever dared to imagine. The universe, it seems, is still very much a work in progress, a grand experiment where the most profound discoveries often lie hidden in the most unexpected of places, waiting for our curiosity to shine a light upon them. We've journeyed through the theoretical and the speculative. Now, let's take stock of our current understanding of the universe's stuff. It's like standing at the edge of a vast, starlit ocean, trying to count every single drop of water, every grain of sand, and every whisper of wind. When we look up at the night sky, truly look, we're seeing the familiar glow of stars, the swirling arms of galaxies, the nebula painting cosmic canvases with their vibrant hues. This is the baryonic matter, the stuff that makes up you, me, the earth beneath our feet, and every atom in those distant suns. It's the tangible, the observable, the universe we can touch, taste, and feel. But here's a humbling thought: this beautiful, shimmering tapestry, this visible universe, accounts for only about 5% of everything out there. Just 5%. It's like finding a single, perfect seashell on an infinite beach. And the rest? Well, the rest is, well, it's dark. About 27% of the cosmos is made up of dark matter. Imagine it as an invisible scaffolding, a gravitational glue holding galaxies together, preventing them from spinning themselves apart like a child's flung frisbee. We can't see it, we can't directly interact with it, but it's there because of its gravitational pull, its silent, unseen influence on the dance of stars and galaxies. It's the ghost in the cosmic machine, its presence felt but its form utterly elusive. We're essentially trying to map a room by only feeling the furniture and never seeing the walls. Then, there's the grandest mystery of all, the silent engine of cosmic expansion, dark energy. This enigmatic force, making up a staggering 68% of the universe, is what's pushing everything apart, accelerating the expansion of space-time itself. It's like a cosmic breath, constantly inflating the universe, stretching the distances between galaxies, a relentless outward push that we're only beginning to comprehend. It's the ultimate cosmic enigma, a pervasive, invisible pressure that dictates the universe's ultimate fate. Think of it as the silent, invisible currents in that vast ocean, shaping its very tides and horizons. So, where does our hypothetical strange matter fit into this grand cosmic inventory? It's a fascinating question, isn't it? If strange matter, with its unique properties, were to exist in significant quantities, it could potentially be a component of dark matter. Perhaps it's a different flavor of that unseen gravitational scaffolding. Or, it might be found in the incredibly dense, exotic environments of neutron stars, those collapsed stellar remnants, where matter is squeezed to unimaginable densities. Could a pocket of stable strange matter, a strangelet, reside within these cosmic titans, a tiny dense island in a sea of neutrons? And this is where the imagination truly takes flight, could it be something entirely new? A fundamental building block that doesn't neatly fit into our current categories, a completely different kind of cosmic ingredient we haven't even conceived of yet. The universe's composition is like a magnificent, intricate pie chart. We've only ever managed to taste, to truly understand a tiny, sweet slice of normal matter. The vast majority, that immense, overwhelming portion, is composed of our dark energy and dark matter, whose fundamental ingredients we are still desperately trying to identify, to name, to understand. Strange matter, in this analogy, is a potential, exotic ingredient for those dark, unexplored slices. It's a whisper of what might be hidden within the shadows, a hint of the truly alien nature of reality. If the universe is so overwhelmingly dominated by the unknown, by forces and substances we can only infer, what does this tell us about the very nature of our quest for knowledge? It's a profound humbling, isn't it? It suggests that our current understanding, as vast as it feels, is merely a flickering candle in an infinite, cosmic night. It highlights the immense frontiers that still lie before us, the vast oceans of ignorance waiting to be charted. It's a call to curiosity, a gentle nudge to keep questioning, to keep exploring, to peer into the darkness with a sense of wonder, not just apprehension. The future of physics, the very unraveling of these cosmic secrets, lies in our willingness to embrace the unknown, to chase the faint glimmers of evidence, and to perhaps, just perhaps, discover that the universe is far stranger and far more magnificent than we could have ever dreamed. The pursuit of understanding is never static. It's a dynamic dance with the unknown, constantly reshaping our perception. And as we've journeyed through the subtle whispers of the universe, we've seen how our very understanding of what makes up reality has undergone these breathtaking transformations. Think back to Newton, that grand architect of the cosmos, who gave us a universe that felt so solid, so predictable, like a perfectly ticking clockwork. His laws of motion painted a picture of a world where everything moved with a certain, graceful certainty. We could trace the arc of a thrown apple, predict the path of a planet, all with a beautiful, almost comforting mathematical precision. It was a universe of billiard balls, colliding and bouncing in predictable ways. But then, the universe, in its infinite wisdom, decided to get a little quirky. It started showing us things that didn't quite fit into that neat, tidy box. And so, we tiptoed into the realm of the quantum. Suddenly, those billiard balls weren't so solid anymore. They became waves of probability, shimmering possibilities, existing in multiple places at once until we dared to look. Particles could be in two states simultaneously, like a coin spinning in the air, neither heads nor tails, but a blur of potential. This was a seismic shift, a complete rewiring of how we perceived matter itself. It was like discovering that the solid ground beneath your feet was, in fact, a vibrant, buzzing dance floor of tiny, energetic beings. And from this quantum awakening, we built the magnificent edifice of the Standard Model. Oh, the Standard Model! It's a testament to human ingenuity, a breathtakingly successful theory that describes the fundamental particles, the quarks, the leptons, the force-carrying bosons, and their intricate interactions. It's like a beautifully woven tapestry, depicting the very threads of existence with astounding accuracy. We can predict, with astonishing precision, the outcomes of particle collisions, the behavior of matter at its most elemental level. It's a triumph, truly. But even the most magnificent tapestries have threads that don't quite match, or perhaps, missing threads entirely. And the Standard Model, for all its glory, leaves us with some profound questions, like echoes in a vast cathedral. It doesn't quite account for gravity, that invisible hand that shapes galaxies and pulls us to the Earth. It's like having a perfect recipe for a cake, but forgetting to include the oven. And then there's the cosmic enigma of dark matter and dark energy. These unseen forces, making up the vast majority of the universe, are like shadows on the edge of our understanding, hinting at realities beyond our current grasp. They're the silent majority, the unseen audience that influences the grand performance of the cosmos. This is where the quest for a unified theory truly ignites our curiosity. It's the dream of a single, elegant framework that can weave together the seemingly disparate threads of quantum mechanics, the realm of the infinitesimally small, and general relativity, the grand architecture of space-time. Imagine a single equation, a single, beautiful principle, that could explain everything. It's like trying to find the master key that unlocks all the doors of the universe. And in this grand search, theoretical physicists, those brave explorers of the abstract, conjure up concepts that stretch our imagination. They play with ideas like a strange matter made of strange quarks, a hypothetical substance that might possess properties unlike anything we've encountered. Even if unproven, these concepts are like the uncharted islands on our evolving map of physics, pushing the boundaries of what we can conceive, inspiring new experiments, new ways of looking. They're the whispers of possibility, beckoning us to explore further. Physics is like a constantly evolving map. We've charted vast territories of known physics, but there are still unexplored continents and oceans where concepts like strange matter might exist. With this constant evolution, What are the most promising avenues for future discoveries related to exotic matter? The quest for understanding propels us forward, towards new tools and experiments designed to probe the universe's deepest secrets. It's a journey, isn't it? A relentless unfolding, like a slow bloom in the cosmic garden. We've spent our time here, on conscious frequency, peering into the heart of strange matter, this enigmatic substance that whispers of the universe's most extreme conditions. But what comes next? Where do we point our collective gaze when the current instruments, as marvelous as they are, can only tell us so much? Well, the future, as always, is brimming with possibilities, and our scientific explorers are already sketching out the blueprints for next-generation experiments. Think of it as upgrading our senses, refining our ability to listen to the universe's faintest melodies. First, let's talk about gravity's whispers. We've become quite adept at catching the ripples in space-time, these cosmic tremors sent out by colliding black holes and neutron stars. But imagine detectors far more sensitive, capable of picking up the faintest gravitational wave signals, perhaps even those originating from the very interiors of neutron stars, those cosmic pressure cookers. These future observatories could unlock the secrets of what happens to matter when it's squeezed beyond all recognition, revealing the true nature of those ultra-dense cores, and perhaps, just perhaps, giving us a clearer glimpse of strange quark matter itself. It's like trying to hear a butterfly's wing beat in a hurricane, but with instruments so finely tuned, we might just catch that delicate flutter. Then there are the particle colliders, those powerful engines of discovery. We've smashed particles together at incredible energies, recreating fleeting moments of the early universe. But the dream is for even higher energies, or perhaps colliders designed to explore entirely different types of interactions. Imagine machines that could probe the very fabric of reality in new ways, potentially creating or detecting entirely exotic states of matter that we can only theorize about now. It's like building a bigger, more powerful microscope, one that can zoom in on the fundamental building blocks of existence with unprecedented clarity, revealing particles and forces we haven't even conceived of yet. And what about the messengers from the cosmos itself? We're talking about cosmic rays, those incredibly energetic particles that bombard our planet. Future detectors are being designed to be exquisitely sensitive, able to identify rare, high-energy particles that might be the fingerprints of the most extreme astrophysical events. Imagine a vast, silent net cast across the sky, waiting to catch the faintest, most energetic whispers from distant galaxies, clues that could point us towards the origins of these cosmic travelers and the extreme environments that forged them. But perhaps the most profound frontier isn't just in building bigger, more powerful machines, but in harnessing the ever-increasing power of computational astrophysics and simulation. Our supercomputers are becoming so powerful, they can essentially simulate extreme cosmic conditions with breathtaking fidelity. We can model the behavior of exotic matter, the crushing pressures of neutron star cores, the chaotic dances of colliding galaxies, all within the digital realm. It's like having a cosmic laboratory in a box, where we can rewind, fast forward, and tweak the universal dials to understand processes that are otherwise impossible to observe directly. Imagine trying to study a hidden ecosystem, a secret world tucked away in the deepest ocean trench, or the highest mountain peak. We're building better microscopes, more sensitive sensors, and more powerful cameras to finally glimpse the unseen inhabitants and processes. These future experiments, these advanced observatories and simulations, are our next generation tools, our upgraded senses for exploring the universe's most profound and enigmatic corners, particularly the realm of strange matter. As we anticipate these future discoveries, what timeless philosophical questions does the study of strange matter ultimately leave us pondering? It's a question that tickles the edges of our understanding, isn't it? When we delve into these extreme states, these possibilities of matter behaving in ways so utterly alien to our everyday experience, it forces us to confront the very nature of reality, of what it means for something to be. Does the existence of such exotic possibilities hint at a universe far more diverse, and perhaps more fluid in its fundamental laws than we currently grasp? It's a beautiful, humbling thought, that the universe might hold more surprises, more fundamental variations on the theme of existence than our current imaginations can fully contain. It makes you wonder, doesn't it, about the vastness of what remains unknown, and the sheer, glorious potential for discovery that lies just beyond our current horizon. Our exploration of strange matter has revealed a universe far more dynamic and interconnected than we might initially perceive. It's like discovering that the quiet, solid furniture in your living room isn't just there, but is actually a slow, patient hum of energy, waiting for the right moment to shimmer and change. We've been talking about these peculiar forms of matter, these cosmic whispers, and it's nudging us towards a deeper understanding of the very fabric of existence. And that fabric, as Einstein so elegantly showed us, is woven from both matter and energy. It's not a case of one or the other, but rather they are two faces of the same ancient coin. Think of it like water. Sometimes it's a solid block of ice, dense and seemingly unyielding. Other times it's a swirling mist, a vapor that can dissipate into the air. Ipimasiu, that beautiful, concise statement, tells us that matter is just concentrated energy. It's energy that has decided to take a pause, to gather itself into a tangible form. And in the extreme environments where we suspect strange matter might dwell, perhaps the crushing hearts of neutron stars, or the swirling accretion disks around black holes, this dance between matter and energy becomes incredibly lively. Imagine a place where gravity's embrace is so fierce, it squeezes the very essence out of things. Here, matter can be condensed from pure energy, like dew forming on a cool morning leaf. Conversely, matter can be unraveled, its tightly bound energy set free, perhaps as blinding light or invisible radiation. It's a constant ebb and flow, a cosmic give and take. This perspective invites us to see the universe not as a collection of isolated objects, but as a vast, interconnected system. Every star, every galaxy, every speck of dust, and yes, even these elusive forms of strange matter, are all participants in an ongoing cosmic conversation. They influence each other, they exchange energy, they shape the grand narrative of the cosmos. It's like a colossal, intricate tapestry, where each thread, no matter how small or unusual, contributes to the overall pattern and strength of the whole. Without the dark threads, the vibrant colors wouldn't have their depth, would they? And this leads us to a truly captivating thought: the potential for hidden structures within the universe. If matter and energy are so fluid, so capable of transforming into one another, what if there are vast reserves of energy bound within forms of matter we simply haven't recognized yet? Imagine a slumbering giant, a reservoir of potential that's just waiting for the right cosmic nudge to awaken. Could some of these exotic forms of matter be, in essence, highly organized, incredibly dense packets of energy, waiting to be discovered, waiting to reveal their secrets? It's like finding an ancient, forgotten library, filled with books of pure light. The universe is like a grand cosmic circulatory system. Energy flows, transforms, and condenses into various forms of matter, including the exotic, all contributing to the overall vitality of existence. It's a system that breathes, that pulses, that constantly reinvents itself. If matter and energy are so intrinsically linked, what does this imply about the fundamental nature of reality and our perception of it? It suggests that perhaps what we perceive as solid and separate might, at its deepest level, be a unified field of potential, a symphony of vibrations waiting to be heard. It's a thought that tickles the edges of our understanding, inviting us to look beyond the surface, to listen to the subtle hum beneath the silence. Our journey has revealed that what we perceive as solid and immutable is, at its core, a dance of forces and fleeting particles. It's a thought that can feel a little dizzying, like standing on the edge of a vast, quiet ocean, and realizing you're not really standing on anything at all, but rather floating, held by invisible currents. Think about the chair you might be sitting on right now. It feels so firm, so unyielding. You can lean into it, rest your weight, and it simply is. But if we were to zoom in far, far beyond what our eyes can ever hope to see, past the wood grain or the fabric weave, we'd find ourselves in a realm that's astonishingly empty. We'd encounter atoms, those fundamental building blocks of everything we know. And the strange, almost comical truth about atoms is that they are, for the most part, vast expanses of nothing. Imagine a grand cathedral with a single, microscopic grain of sand at its very center. That grain of sand is like the nucleus, the dense heart of the atom, and the rest of that immense cathedral. That's the electron cloud, a hazy, probabilistic dance of energy, spread out over an enormous, empty space. So, when you touch that chair, you're not really touching solid matter in the way we usually imagine. You're experiencing the thus repulsive force of electron clouds bumping into each other, a kind of gentle, energetic handshake that prevents you from passing through. And this incredible phenomenon, this very solidity that underpins our everyday reality, is governed by one of the universe's most peculiar rules, the Pauli exclusion principle. It's a quantum mechanical law that essentially says no two identical fermions, like electrons, can occupy the same quantum state simultaneously. Think of it like assigned seating at a cosmic concert. Each electron has its own unique ticket, its own specific seat in the atom's energetic stadium. They can't all cram into the same row, the same seat. This principle is what creates the distinct shells and energy levels within atoms, and it's this very arrangement, this determined separation, that gives matter its structure, its form, and yes, its apparent solidity. It's the universe's way of saying, everyone gets their own space. And now, let's let our minds wander to the truly exotic. We've touched on the idea of a strange matter, hypothetical substances made of up and down quarks, but also containing strange quarks. If such matter were to exist and remain stable, it would represent an extreme departure from our everyday understanding of density. Imagine matter so incredibly compressed, so tightly packed, that the very concept of empty space within its atoms would be radically redefined. It would be like taking that cathedral and squeezing it down until the grain of sand was no longer just in the center, but the entire structure was the size of a pinprick, yet still retaining all its original, stuff. The forces holding it together, or perhaps the absence of forces pushing it apart, would be operating on principles far beyond our common experience. And this brings us back to ourselves, to our own perception. Our senses are remarkably adept at translating the complex quantum interactions of these fundamental particles into the familiar, tangible world we navigate. The deaf feeling of solidity, the wa sight of a solid object, the s sound it makes when it bumps into something, these are all interpretations. Our consciousness, in its beautiful, intricate way, weaves together the data from these interactions, these energetic nudges and repulsions, and constructs a narrative of a solid, stable reality. It's like mistaking the intricate patterns of a flowing river for a solid path. The underlying reality is dynamic, not static, and this is even more true for exotic states of matter. The river's currents are always shifting, always moving, and so too are the fundamental constituents of what we perceive as solid. If solidity is, in essence, an emergent property, a sophisticated dance of quantum rules and energetic interactions, what does this suggest about the potential for consciousness to interact with reality at a more fundamental level? If the very fabric of what we call solid is so fluid and interconnected, could our own consciousness, in its unique energetic signature, find ways to resonate with these deeper frequencies, to influence or even us traverse these seemingly fixed boundaries? It's a thought that opens up a universe of possibilities, a gentle invitation to question the very nature of what we hold to be true, and to wonder about the unseen connections that bind us all. We've danced at the edges of the universe's extremes, from the silent ballad of nebulae to the explosive birth of stars. Now, let's descend, if you will, into the quantum realm, the true birthplace of strangeness, a place where the very fabric of reality hums with an almost musical unpredictability. It's like stepping from a grand, ordered ballroom into a bustling, vibrant marketplace where the rules of physics are more like suggestions. At this incredibly miniature scale, far beyond what our eyes can ever perceive, things aren't quite as solid and predictable as our everyday experience might suggest. We encounter quantum fluctuations. Imagine the surface of a perfectly still lake, so calm you can see your reflection with crystalline clarity. Now, zoom in impossibly close, until you're looking at the water molecules themselves. Even there, at the very edge of existence, there's a subtle, ceaseless shimmering. Energy isn't just there, it's constantly bubbling into and out of being. Particles wink into existence for the briefest of moments, born from this inherent uncertainty, only to vanish back into the void. It's like tiny sparks of possibility, flitting in and out of the darkness, a constant, energetic dance that underlies everything. And then there's superposition. This is where things get truly mind-bending. A particle, before it's observed, can exist in multiple states, in multiple places, all at once. Think of a coin spinning in the air. Until it lands, it's neither heads nor tails, it's in a state of both. But in the quantum world, it's not just a metaphor, it's the literal reality. A tiny electron can be spinning clockwise and counter-clockwise simultaneously, or be in this location and that location at the exact same instant. It's as if reality itself hasn't quite decided what to make of it yet, holding all possibilities open until an interaction, an observation, forces it to pick just one. Closely tied to this is entanglement. Imagine two of these spinning coins, somehow linked. If you measure one and find its heads, you instantly know the other. No matter how far away it is across the room, across the galaxy, must be tails. They are, in a way, still one entity, sharing a destiny that transcends space. It's a connection so profound, so immediate, that Einstein famously called it spooky action at a distance. It's like having two perfectly synchronized dancers who, even when separated by an ocean, mirror each other's every move without any apparent signal passing between them. Now, to understand how matter behaves under the most extreme conditions, especially when we're talking about something as unusual as strange matter, we often delve into the realm of quantum chromodynamics, or QCD. This is the theory that describes the strong nuclear force, the glue that holds the very heart of atoms together. It's all about quarks and gluons, the fundamental building blocks that make up protons and neutrons. These particles are rarely found in isolation. They're always bound together by these incredibly powerful gluons, forming a sort of sticky energetic plasma. Think of it like trying to pull apart a handful of incredibly strong, elastic bands that are constantly snapping back. QCD helps us understand how these forces behave, especially in environments where matter is compressed or energized to an extraordinary degree, like in the heart of a neutron star, or perhaps within strange matter itself. And all of this, the fluctuations, the superposition, the entanglement, happens within what we call the S-quantum vacuum. It's a curious concept, isn't it? We tend to think of empty space as just emptiness, a vast, silent void. But in the quantum world, this vacuum is anything but empty. It's a seething, energetic field, teeming with potential. It's a fertile ground where these transient particles, these virtual particles, are constantly popping in and out of existence. It's like an ocean floor, seemingly still and quiet, but beneath the surface, there's a constant, gentle churn of currents and unseen life. This vacuum isn't a passive backdrop, it's an active participant, a source of energy and possibility. So, you see, the quantum realm is like a vast, shimmering sea of potential, where waves of energy can momentarily coalesce into particles, only to dissolve back into the flux. It's here that the rules of ordinary matter are rewritten, where the solid ground beneath our feet dissolves into a dance of probabilities. It's a realm of profound mystery, where the very act of looking can change what you see. And this leads us to a truly fascinating thought. If this quantum flux, this inherent uncertainty, is so fundamental to the universe, so woven into its very being, could the peculiar properties of exotic matter, like strange matter, be intrinsically linked to these inherent uncertainties? Could the very strangeness we're exploring be a direct consequence of the universe's deepest, most fundamental hum? It's a question that whispers at the edge of our understanding, inviting us to peer a little deeper into the heart of what makes reality, well, real. The universe, in its grandest sense, is governed by fundamental laws of thermodynamics. How might strange matter fit into this cosmic balance? It's a question that tickles the edges of our understanding, like trying to grasp smoke with your bare hands. You see, the universe has a rather persistent habit, a deep-seated tendency, if you will, to move towards disorder. This is the essence of the second law of thermodynamics, a law as fundamental as gravity itself. Think of a perfectly stacked deck of cards. Leave it for a while, and it's more likely to get shuffled, to become a chaotic mess, than to spontaneously reorder itself into a pristine sequence. That tendency towards disarray, that increase in entropy, is a one-way street for most natural processes. It's like a gentle, inexorable tide pulling everything towards a state of greater randomness, a diffusion of energy, a blurring of sharp distinctions. Now, matter itself, in all its glorious forms, is really just a manifestation of energy arranged in particular ways. From the delicate dance of electrons in an atom to the swirling chaos of a galaxy, each state of matter is a unique thermodynamic configuration. Solids, liquids, gases, they're all just different ways energy can be parceled out and organized among particles. Think of water, frozen into ice. It's a rigid, ordered structure, a tightly held embrace of molecules. As a liquid, it flows, its molecules sliding past each other with a bit more freedom. And as steam, it's a wild, energetic ballad, molecules zipping about with boundless abandon. Each transition, each change of state, involves a shift in energy and a rearrangement of particles, a journey along the thermodynamic landscape. And this is where things get truly fascinating when we consider extreme environments. Imagine the crushing pressures inside a neutron star, or the searing, primordial soup of the early universe. In these places, the usual rules seem to bend, to warp under the immense forces at play. The sheer density, the colossal temperatures, can create thermodynamic equilibria that are utterly alien to our everyday experience. It's in these crucible-like conditions, where matter is squeezed and battered beyond recognition, that we might find the universe naturally settling into its most stable, lowest energy configurations. And a strange matter, with its hypothesized unique stability, could very well be one such configuration. It's like finding a perfectly balanced stone on a windswept mountain. It's there, because the forces have sculpted it into that particular, enduring form. Thermodynamics is like the universe's natural tendency to seek balance. Just as heat flows from hot to cold, matter under extreme conditions might naturally settle into its most stable, lowest energy configuration, which could be strange matter. It's a cosmic preference for peace, for a state of least resistance, even if that state looks utterly bizarre to our limited perspective. It's as if the universe, when pushed to its limits, whispers its deepest secrets, revealing the fundamental arrangements that can withstand the most intense scrutiny. And this dance with equilibrium, this universal quest for balance, it also informs our understanding of the universe's ultimate fate. Will it continue to expand and cool, eventually reaching a state of ultimate, uniform emptiness, a cold, dark diffusion of energy? Or will it perhaps collapse back upon itself, a cosmic sigh before another great inhale? Thermodynamics paints a picture of a universe in constant, slow motion, a grand, unfolding story written in the language of energy and order. If the universe seeks equilibrium, what does this imply about the fundamental constants that govern its behavior? Are these constants themselves a reflection of some deeper, universal equilibrium? A set of finely tuned knobs that allow for the existence of everything we see, and perhaps even the strange matter we only glimpse in theory? It's a thought that hums in the quiet spaces, a question that invites us to look beyond the obvious, to the subtle, underlying principles that shape reality. The delicate balance of the universe, it's orchestrated by these fundamental constants. These aren't just numbers in a textbook, they're the very scaffolding upon which reality is built. Think of them as the invisible strings of a cosmic harp, each vibrating at a precise frequency, and together, they create the melody of existence. Could these constants, these seemingly abstract values, be the very architects of exotic matter's possibility? It's a thought that tickles the edges of our understanding, isn't it? So, what exactly are these fundamental constants? We're talking about things like the speed of light, that ultimate cosmic speed limit, a silent, unwavering decree. Then there's Planck's constant, a tiny, almost impossibly small number that governs the granular nature of energy, the quantum whispers that underpin everything. We have the gravitational constant, the silent hand that pulls galaxies together, that keeps our feet planted firmly on this spinning planet. And of course, the masses of fundamental particles, the electrons, the quarks, those tiny building blocks, each with its own unique heft. These are the bedrock, the unchangeable parameters that define our universe. Now, here's where it gets truly fascinating, and a little bit humbling. This is the fine-tuning problem. Imagine if you were to slightly nudge one of these constants, just a whisper, a breath of change. The universe as we know it would simply unravel. If the gravitational constant were even a tiny bit stronger, stars would burn out too quickly, perhaps never even igniting. If it were weaker, they might not form at all. If the electromagnetic force were just a hair different, atoms themselves might not be stable. Imagine a universe where electrons couldn't bind to protons, where chemistry, as we understand it, was an impossibility. No stars, no planets, no us. It's like a cosmic recipe where every ingredient must be measured with absolute, unfathomable precision. And how does this relate to our strange, captivating quark matter? Well, these constants dictate the very forces that hold quarks together, and the energy scales at which they can exist. The strength of the strong nuclear force, for instance, is a constant. The masses of the up, down, and strange quarks are also constants. If these values were different, the delicate dance of quarks within protons and neutrons, or their potential to form new, exotic configurations like a strangelets, would be entirely altered. A slightly weaker strong force, or a different mass for the strange quark, might mean that strange matter could never form, or conversely, that it would be the dominant form of matter. It's as if the constants are setting the stage, dictating the very possibility of these unusual states of matter emerging from the quantum foam. The universe's fundamental constants are like the precise tuning of a grand piano. If even one string is slightly off, the entire symphony sounds wrong. The strangeness of matter, its very existence and potential stability, is a direct consequence of this precise tuning. It's a symphony played on instruments tuned to an unimaginable degree of accuracy. This leads us to some profound philosophical questions. If the universe is so finely tuned, what does this suggest about the underlying order, or even purpose, of existence? Some might look at this and invoke the anthropic principle, the idea that the universe must have properties that allow for conscious observers to exist within it, because, well, here we are. Others might suggest of a multiverse, an infinite tapestry of universes, each with its own set of constants, and we simply happen to reside in one that's hospitable to life, and perhaps to strange matter. It's like finding a perfectly formed seashell on the beach. Is it a miracle, or just one of countless shells shaped by the tides and currents of existence? The constants, in their silent, unwavering authority, invite us to ponder these vast cosmic questions, to gaze out at the starlight and wonder about the unseen hands that might have tuned the universe to such exquisite, and at times, strange, perfection. As we draw our journey towards its gentle close, let us weave together the threads of science, philosophy, and wonder. It's a beautiful thought, isn't it? That all these disparate pieces of existence, from the most exotic theoretical concepts, like strange matter, to the very fundamental forces that bind the universe together, to the quiet hum of our own consciousness, and even the grand, sprawling story of cosmic evolution, they're not separate tales at all. They're all chapters, intricately bound, within a single, magnificent narrative. Imagine it like a vast, ancient tapestry, woven with threads of starlight and shadow, each strand a testament to a different aspect of the same, unfolding reality. And this universe, it feels less like a static, pre-built machine and more like a living, breathing entity. It's constantly in motion, a gentle, ceaseless dance of creation and transformation. New possibilities are always bubbling up, like seeds carried on a cosmic wind, finding fertile ground in the vastness of space and time. It's a self-organizing system, a grand experiment that's always learning, always evolving, always surprising itself. Think of a vast garden, where every bloom, every rustle of leaves, every tiny insect is part of a complex, interconnected life. Our universe feels much the same, a garden of immense proportions, teeming with unimaginable beauty and potential. And what fuels this magnificent unfolding? It's that little spark, that persistent whisper in our minds, the drive to ask, what if? Curiosity. It's the most essential tool we possess, isn't it? It's the gentle nudge that pushes us beyond the familiar, the quiet quest that opens doors to understanding. Without it, we'd be like ships anchored in a calm harbor, never knowing the vastness of the ocean that awaits. It's the very engine of discovery, the compass that guides us through the uncharted territories of knowledge. But even as we push the boundaries, as science unveils more and more of its secrets, there's a profound beauty in acknowledging that the universe will likely always hold profound mysteries. It's not a failing of our intellect, but rather a testament to the sheer, boundless immensity of existence. These mysteries aren't walls to our understanding, but rather invitations to awe, to a deeper sense of wonder. They're like the faint, distant stars we can't quite resolve, hinting at even grander spectacles beyond our immediate grasp. The universe is not just a collection of parts, but a single, magnificent symphony. Each note, from the familiar hum of an atom to the theoretical resonance of strange matter, contributes to the overarching harmony. It's a melody that has been playing for eons, and we, in our own unique way, are part of that song. As we prepare to transition from this exploration, what final thoughts can help us carry this sense of wonder and peace into our resting state? Perhaps it's simply to remember that we are not isolated points of light, but rather vibrant strands in this grand cosmic tapestry, each with our own unique frequency contributing to the beautiful, intricate symphony of existence. We have explored the hidden forces of strange matter, and in doing so, perhaps glimpsed something of the extraordinary forces within ourselves. It's a curious thing, isn't it? We've been peering into the cosmic dark, into the realm of particles that defy our everyday understanding, and in that very act, we've been invited to look inward. The universe, in its boundless, enigmatic sprawl, holds a mirror to our own inner cosmos. Think of it, the vast, uncharted territories of space, peppered with phenomena we're only just beginning to name, feel remarkably like the landscape of our own minds. There are galaxies of thought we haven't yet visited, nebulae of emotion that swirl in colors we can't quite describe, and dark matter, perhaps, in the form of unconscious patterns that shape our every step. This journey into the peculiar properties of strange matter, this dance with the unknown, it's also a gentle reminder of the universe's infinite capacity for transformation. Just as exotic matter hints at possibilities beyond our current grasp, at states of being we've only dreamed of, so too does our own consciousness hold this profound potential. Imagine a seed, dormant in the earth, holding within it the blueprint for a towering oak, or a vibrant bloom. That's the kind of latent power we're talking about. The very existence of these strange particles, these whispers of what could be, echoes the potential for profound change that resides within each of us. It's the quiet hum of possibility, the subtle vibration of becoming. And there's a particular kind of quiet resonance that comes from contemplating these deep truths, isn't there? It's not the thunderous revelation, but more like the soft unfolding of a petal, or the gradual warming of the sun on your skin. Even when these concepts remain partially out of reach, like distant stars whose light has traveled for eons to reach us, there's a deep satisfaction in simply acknowledging their existence, in letting their light filter into our awareness. It's the pleasure of knowing that the universe, and ourselves, are far more intricate and wondrous than we might initially perceive. It's like finding a perfectly smooth stone on a beach, its edges worn soft by the endless rhythm of the waves. So, as we prepare to gently transition from this particular exploration, I invite you to carry something with you. Carry that sense of awe, that spark of curiosity that has been kindled. Don't let it flicker out like a dying ember. Keep it alive, like a precious candle in a quiet room. The universe is like a vast, quiet library. We've spent time in one fascinating section, the section on strange matter, but countless other volumes, holding even deeper stories and truths, await our gentle exploration. And the most fascinating library of all, of course, is the one within you. As we prepare to transition, take a moment to acknowledge one new thought or feeling that has emerged for you during this journey. Perhaps it's a sense of wonder about your own inner universe, or a quiet recognition of your own potential for transformation. Just notice it, without judgment, and let it settle. This is the beginning of carrying the wonder forward. We have journeyed together, from the theoretical whispers of strangelets, to the powerful embrace of fundamental forces, from the dense cores of neutron stars to the subtle interplay of consciousness in the cosmos. We've touched upon the science, the philosophy, and the sheer wonder that such concepts evoke. We've considered the possibility of matter so dense, so alien, that it could reshape reality itself, and pondered how such cosmic oddities might whisper secrets about the very fabric of our existence, perhaps even hinting at a deeper connection between the universe's most extreme states and the quiet hum of our own awareness. It's been a voyage through the edges of what we know, and into the luminous twilight of what we can only imagine. This exploration serves as a beautiful reminder that our current understanding is but a snapshot of an infinitely complex reality. The universe is a poem yet to be fully read, a song with melodies we are only beginning to discern. The concept of strange matter, this hypothetical substance born from the most extreme cosmic pressures, encourages us to look beyond the familiar, to appreciate the sheer vastness of possibility that lies just beyond our immediate perception. It invites us to embrace the mystery, to find peace in the vastness, and to recognize the profound and interconnectedness of all things, from the smallest quark to the grandest cosmic dance. It's a gentle nudge to remember that even in our quiet moments, we are connected to these immense cosmic processes, part of an unfolding story far grander than we can easily grasp. I invite you now to share your own reflections on this journey in the comments below. What resonated most deeply? What new questions have bloomed within you? Let us continue this conversation, fostering a community of shared curiosity and gentle inquiry. And if you feel called to, please subscribe to join our continuing explorations, to keep the lamp of wonder lit together. As this exploration gently concludes, allow yourself to drift. Feel the gentle rhythm of your breath, a soft anchor in the quiet. Release any lingering thoughts, and surrender to a state of deep peace. May your rest be profound, your dreams be serene, and your return to wakefulness be as gentle as the dawn. Sleep well, dear traveler. Good night.